discuss exhaustive proof and proof by cases. In discrete mathematics, both exhaustive proof and proof by cases are common techniques used to establish the validity of statements, propositions, or theorems. Now, let's see how these methods are applied into the realm of mathematics. Exhaustive proof in discrete mathematics involves demonstrating that a statement holds true by considering every possible case or scenario within a finite domain. This method is particularly applicable when dealing with finite sets, combinations, permutations, or any situations where the number of cases is manageable. For example, statement every positive integer is either even or odd. Exhaustive proof. Definition of even and odd. An integer n is even if it can be expressed as twice some integer k. An integer n is odd if it can be expressed as twice some integer k. So, the exhaustive. Consider every positive integer. If n equals 1, then n equals 1 odd. If n equals 2 and n equals 2, it's even. If n equals 3, n equals 3, it's odd. If n equals 4 and n equals 4, it's even, and so on. By exhaustively checking every positive integer, we see that each one falls into one of two categories, even or odd. Proof by cases. It involves breaking down a problem into different scenarios or cases and proving that the statement holds true for each case. This method is useful when a problem can be naturally divided into distinct situations, and proving each situation separately is simpler than proving the entire statement directly. For example, consider the statement for any integer n, if n is even, then n squared is also an even number. So here's the answer. Case 1. N is even. If n is even, then by definition, n equals 2k for some integer k. Squaring n gives n squared equals 2k squared equals 4k squared. Since 4k squared is clearly divisible by 2, n squared is even. So in case 2, n is odd. If n is odd, this case is irrelevant to the statement because the statement only concerns even n. We do not need to prove anything about n when n is odd for this particular statement. Since we have demonstrated that n squared is even in the only relevant case, if n is even, we can conclude that the statement is true for any integer n. If n is even, then n squared is also even. In summary, both exhaustive proof and proof by cases are crucial in different contexts. Exhaustive proof provides complete, certainty, and manageable scenarios, while proof by cases offers a structured way to handle complex or infinite scenarios systematically.
Good day everyone. Good day Sir Nasbin. I am Rosemaya Makabudbud from Group 14 and I'm going to report the existence proof, which is one of the topics in proof methods and strategy. So before we proceed on discussing about our topic for today, so let me give you one scenario that can relate to the existence proofs. So suppose you have a squirrel named Flufftail as a pet. One day, while you're talking to a friend about Flufftail, a stranger overhears you and points out that the squirrel is a rare animal to have as a pet. He then goes on to tell you that because it is so rare, he doesn't believe that Flufftail exists. To which you reply that Flufftail certainly does exist and you can prove it. Believe it or not, this scenario has some mathematical significance. You see, in mathematics, proving that Flufftail exists would be considered as an existence proof. So when a theorem states that an element, we call it X, exists that satisfies a certain property, we call the theorem an existence theorem, and the proof of the theorem is called an existence proof. For example, first, there exists a real number x such that 2x minus 6 equals 8. Second, there exists a prime number p such that p plus 8 is also a prime number. So let's remember that existence proofs are used to show that there exists at least one object with the specific properties. So mathematicians use special notations for this, as you can see. So in constructive proof, it is produce a particular x such that px is true. In non-constructive, prove that there is an x such that px is true without actually producing it. Okay, for example, there exists a real number x such that 2x minus 6 equals 8. To prove that this statement is true, find or construct a number x that satisfies the equation 2x minus 6 equals 8. You could use trial and error to find an x that gives a true statement. You could also use algebra and actually solve for x in this equation. Solving f or x, 2x minus 6 equals 8. So add 6 to both sides. Then it became 2x equals 14. Divide both sides by 2. And the result is x equals 7. So by solving for x, you get x equals 7. Therefore, you have found a real number that makes the equation true. Moving on to the non-constructive proof, from what I have discussed earlier, so it is a proof which indirectly shows a mathematical object exists without providing a specific example or algorithm for producing an example. So here is an example for the non-constructive proof. So the statement is, in a room with 367 people, there must be at least 2 people who share the same birthday, including leap years. So in non-constructive proof, there are only 366 possible birthdays in a year, 365 days for regular years, and 1 extra for leap years. If there are 367 people in the room, that's 1 more person than the number of possible birthdays. So why is this non-constructive? So this proof shows that at least 2 people share a birthday, but it doesn't tell us who those people are. So we only know it must be true based on the limited number of birthdays compared to the number of people. The attached picture here is another example of non-constructive existence proof, so that we can really understand what is non-constructive, and we can also differentiate it from the constructive proof. And that's all for my topic. I hope you learned something, and thank you for listening.
Proof strategies are fundamental in the realm of mathematics, guiding mathematicians in the art of proving theorems and propositions. When delving into the realm of 1.8.5 proof strategies, several key aspects come to the forefront. Firstly, an introduction to proof strategies sets the stage for understanding the various techniques and approaches used in mathematical proofs. It serves as foundation for mathematicians to navigate the intricate path of logic and reasoning to establish the validity of mathematical statements. Forward and backward reasoning are two pivotal techniques within proof strategies. Forward reasoning involves starting from the premises and logically progressing towards the conclusion, step by step. On the other hand, backward reasoning begins with the desired conclusion and works backward to identify the necessary steps and premises to reach the endpoint. Both methods play a crucial role in constructing sound and rigorous proofs. Adapting existing proofs is another significant facet of proof strategies. Mathematicians often encountered problems that bear similarities to previously solved theorems. In such cases, adapting existing proofs involves modifying and applying known proof techniques to address new challenges, thereby leveraging prior knowledge to tackle novel mathematical problems efficiently. In essence, 1.8.5 proof strategies encapsulate the essence of mathematical reasoning, emphasizing the importance of logical thinking, creativity, and adaptability in the pursuit of establishing mathematical truths. In the realm of 1.8.5 proof strategies, let's delve into an example to illustrate the importance of key elements such as an introduction to proof strategies, forward and backward reasoning, and adapting existing proofs. Imagine we want to prove that the statement the sum of two even integers is always an even number. To start, we introduce proof strategies as the systematic methods used to establish the validity of mathematical statements. This sets the stage for our proof journey. First, let's apply forward reasoning. We begin by taking two even integers, say 2 and 4. We add them together to get 6, which is also an even number. By continuing this process with any two even integers, we consistently arrive at an even sum. This logical progression from premises to conclusion exemplifies forward reasoning in action. Next, let's explore backward reasoning. Starting with the conclusion that the sum of two even integers is even, we work backward to identify the properties that ensure this outcome. By recognizing that the sum of two even numbers always result in a number divisible by 2 without remainder, we establish the validity of our claim through backward reasoning. Lastly, adapting existing proofs comes into play. Drawing from the known properties of even numbers and leveraging proofs related to divisibility, we adapt these existing concepts to demonstrate the validity of our statement. By building upon established mathematical truths, we construct a robust proof that solidifies the assertion that the sum of two even integers is indeed always an even number. In this example, we witness how an understanding of proof strategies, coupled with forward and backward reasoning and the adaptation of existing proofs, enables us to unravel the mysteries of mathematical truths and reinforce the foundations of mathematical reasoning.